So we're going to continue on with CT. Again, here's this list of additional text. I don't know if you've looked any of these up, but sometimes on Amazon or other places, you can get these secondhand for a real deal. So they once in a while, one will pop up for like $5. And so you should, so I now have 3 copies of CAC and Sling, but anyway. So if imaging is in your future, these are good books. So carrying on with our discussion of sampling rate and what is an adequate sampling rate for CT. We'll take a look at that today. And remember, there's 2 things we can change in order to change the sampling rate for our CT scanner, and that is, remember the GL theta function, which is our raw data. We can sample in the L direction. So that's along the detector array. That's usually about 1,000 detectors in that row. And we can also sample a variable number of angles. And if you've been messing around with the MATLAB script that I sent out and tried reconstructing a picture with, say, 12 angles, right, you can see what the result is, right, as opposed to using 300 or something sensible. With the sampling rate in L, in the early incantation of CT, where we had a source and we raster that source across the patient and we sample the attenuation of the X-rays with a single detector as we're going across, this would correspond to what displacement would we use between each one of those views, right? Or temporally, if we raster this thing continuously, what's our rate in time of taking samples from this detector? There's 2 other things that are going to affect resolution. Remember, one is the spot size of the creation of the X-rays. Ideally, they would come from an infinitesimally small spot. They don't. And also the width of this detector, right? If the detector itself is quite wide, then that will limit your spatial resolution in detecting from where did this beam come from in the patient, right? When you look above. And that's fairly commonsensical. You can just look at it and say, look, if I have a really wide detector, then beams can be coming from all different angles into that detector, and so I'm blurring the signal from my object. Then we rotate some angle delta theta, and we do the whole thing again. So we get to choose that angle. We get to choose how many of those projections we're going to make. And so today what we're going to look at is, how do you decide what is the appropriate number of those projections to make? And if my final image, let's say my final image is going to be a 512 by 512 matrix of point estimates of the attenuation coefficient at each one of those points in space or inside a little box. A 512 by 512 matrix, how many angles do you think you would need, just off the top of your head? Let's take a guess. Would it be 5,000? Would it be 5? Would it be 500? It's probably around 500, right? Somewhere in that order, right? It's like if you were to just see the density of points there and say, I got to click and measure a whole new set of points and click and measure a whole new set of points. It's going to be in that order, magnitude-wise. It's not exactly that, but it'll be somewhere in that order. Right? Okay. Modern detectors are not designed like this, where you raster across the patient. They're designed like this so that you obtain all of your data very quickly at many angles and through many slices simultaneously. To date, all we've really looked at in terms of understanding reconstruction is this middle case here, this case, where we've looked in 2 dimensions, right? We have G, L, theta. We haven't really looked at what the consequences are of having a cone of X-rays in the Z direction, and we won't. But in looking at, the resolution here, we have to ask, like, what is the benefit of, say, using twice as many detectors in this dimension? So I've got 1,000. What would the benefit of having 2,000 be? Right? Does that give me a much better spatial resolution in my final image that lets me see things that I couldn't see before? Right? So that's that sampling issue. For many years, the sort of center to center distance between these detector elements in CT detectors has been 1 millimeter. Really hasn't changed much over about 25 years or something, is that has been considered to be, good enough. And what has changed is the fact that they stack many more of these things on top of each other. And so over the last 20 years, this dimension has increased by orders of magnitude. So it started out as 1, it went to 4, then it went to 8, 16, 32, 64. And finally, one manufacturer made one with 320 in this direction. And it's a little more complicated when you have, your X-ray beams going off in angles in Z, right? So, but we're going to principally focus on the center of this detector, and we're down to 1D here. So what I'm going to show in the next few slides here, you can achieve yourself with that little script I gave you to look at how changing sampling affects CT image quality. And so here I've set it up such that we're going to get a 256 by 256 image, and the image that results when you put noise on top of the data and then reconstruct using 45 angles, right, for a 256 by 256 image, is you get this image here. Okay, now remember, this image has little dots. In fact, this one, I forget precisely whether or not these dots have a separation between them to try and measure resolution, or they're single dots. But this is the noise-free case, and this is what it looks like when you have noise on the raw data. So obviously there's some kind of structure in the noise as we look in the field of view here, and also over here, we have a lot of artifacts because we've obviously undersampled in the theta direction, right? So remember, if I took 2 angles, I would have 2 big streaks across the field of view, right? And as I get more and more angles, those streaks add up in number, right? So I get many more streaks across the field of view. However, because of the negative side lobes on our convolution filter, those streaks start canceling each other out. And so if you take enough projections and you put enough of those streaks that have a negative side lobe and a positive thing, they'll just cancel themselves right out. And that's where you get to the analytical solution with that ramp function in Fourier space, or the convolution of that inverse Fourier transform of the ramp function, and do convolution back projection. You get back the original object. We're doing this in a discrete way, though. We're going to take a finite number of those angles as opposed to a continuous integral of those angles, right? And so 45 views gives us this picture here. If we go up to 90 views, the picture changes, obviously. This changes. Let's just look at the raw data. That's 45 views. That's 90 views. Okay, so 45 views, you see you have steps along here, etc. 90, we start getting a better continuous estimate of that sine wave in the sinogram. The image itself looks quite different. The streaks are more closely packed, which makes sense, right? And it seems like the image is more accurate in certain areas, right? Where the streaks are actually canceling things out sort of more accurately. And we look at the background noise, and this background noise in the outside or the periphery also obviously has some interesting structure to it. Whereas the noise right at the center looks like, well, it could be just a random blob, right, at the center and in the middle. So some kind of spatial change in how the noise field looks when you increase the number of views. So let's keep going. We'll do 180 views. So let's go toggle back and forth. That's 90. This is 180, right? And now it's starting to look like a reasonable picture, right? So things have kind of canceled each other out. We're getting close to the dimension of our picture itself. The number of pixels that we're trying to estimate and the number of angles is starting to be roughly the same, right? However, you can still see there does seem to be a structure outside here compared with the central part of this image, right? And this is due to the fact that the density of those back projections is just higher in the middle, right? So when you back project and a projection goes through the center, which they all do, right? You get a higher density of those projections in the middle. And so the fidelity of the estimate in the center of the field of view is better when you have this condition of fewer views, right? If we just keep increasing views, so go to 360. So now I've pretty well eliminated all of my streaks out here. And this looks pretty uniform everywhere, yes? Yeah.
So other than the computational requirements, is there a reason why we can't keep going up the number of views, for example, with overfit after a point?
Yeah. Okay, so the question is, why not do 10,000 views, right? I mean, if we're just getting better and better, why not just take more and more views? And that is possible because the way the data is collected is the X-rays are turned on and the gantry rotates continuously and the sampling occurs continuously in time, right? It's not like we're stopping the gantry, taking data, stopping the gantry, taking data. So it's just taking, so if we up the time, rate of our sampling, we could get many more views, right? Eventually, what's going to happen though with each one of those views? If it now goes down to picoseconds and I have many views, thousands of views, what's the problem with each of those views? Say again? You got to ship all that data out, right? Which is one thing. So there's a limit on how fast you can ship data off the scanner. That's absolutely true. But there's something fundamental about the projections themselves, yeah? Well, the ones one beside the other will look remarkably similar, right? That's true. And so they're kind of redundant after a while, particularly if your projections, say I have 1,000 detectors, right? And when I take 10,000 views, my detector actually moves 1/100th of a detector distance. Is that really any different than where it was, right? So there's that. But then the other question is, we're going to run out of what? Well, we could run out of memory. Yes, it's true. There's something else we're going to run out of in each projection, though. And this is a fundamental thing. If you remember anything about CT, this is a really fundamental thing. Say again? We run out of signal. What is the signal? Photons, right? So a signal is generated by a photon hitting the detector, making a flash, right? So if I take 100,000 views, how many flashes do I get per view? Not that many, right? So eventually I just run out of photons. I have a finite number. And so you do want to, and this is usually done with the current adjustment in the X-ray tube. So you make your X-ray fluence and the rotation of the gantry such that you get a reasonable number of photons in each view, right? So that's one limiting factor, right? If you wanted to keep cranking the MA up, you could get to a reasonable number of photons in each view, but then you're using more dose. Signal to noise of the picture would be beautiful, right? But do you need it, right? So the other thing is, eventually, when you add 2 more views, your resolution will not change, right? Because your resolution is fundamentally limited by the size of the X-ray spot and by the dimension of the detector element itself, right? And so you can imagine that one reasonable way to do samples would be to take a projection every time the detector moved a unit of the detector array. That's one way to think of it, right? At least the whole thing shifts over by 1 unit, right, in the detector space. But eventually, as we go to higher and higher numbers, I don't know if I have a higher one here. Well, I do. Look, here's 720. So things do change a little, right? But principally what is happening here, because I haven't normalized like to the number of photons per projection, is that the noise just went down, right? So it's just like, I get the same picture. It's just like averaging 2 of them together between here and here, right? So if I go back 360, 720, the character of the image doesn't change, the artifact and everything. It's just the noise level is going to go down because we're just averaging more projections together. That is under the assumption that the noise here is constant, right? If I go to 720 views by sampling for half as long, then I've got other issues because I haven't modeled that here, that the number of photons is going down, right? So you have to take that in consideration. So let's take a look. Let's go back to 180 views. We see that there's artifact at some points in this field of view. We see that the noise has a strange looking characteristic out here versus inside here, the noise looks just kind of like a random white noise field. There aren't correlations the way there are these correlations in theta out here, right? And that, yeah, that looks even better on your screen actually, because this one blurs it a bit. So it's you can see that the difference. So just gestalting this, it looks like there is a field of view within which this is an adequate number of views. Like to reconstruct whatever's inside this circle, probably an adequate number of views. Outside here, not so much, right? So let's see, we can take a look at that. And zoom that up, and you can see the artifacts out in the periphery. Inside here, it looks like we have some kind of nicely behaved noise field. This is called view aliasing. Like these artifacts are from undersampling in theta. But the best way to look at these, okay, this is just to set up the next picture. So these are individual projections. They're convolved. After the convolution, they look like this, and the back projection makes them look like this. This is from Cack and Slaney. And similar to what we just looked at, only with a much simpler object and much more severe undersampling, we have number of projections in this direction, and we have samples per projection in this direction, right? So let's say we do 512 projections and we have 512 samples, we get this picture, right? As we reduce the number of projections, we start getting these very odd looking patterns that analytically we can derive for this simple object, right? And these patterns obviously aren't in the object. They are the interference of all these side bands, you know, or in the point spread function that are interfering. And then as we reduce the samples per projection, so we just, you know, along the L direction, we just cut the number in half, then cut it in half, then cut it in half, we get undersampled like this. So we get these very large streaks, right? So that's sort of the whole space and what it looks like. Now remember, I guess a few lectures ago now, we looked at the Nyquist criteria for sampling along L, right? Where if we have a sine wave of a certain frequency and we want to make sure that that frequency is included in our sampling, then we need to sample at twice the frequency, right? So the Nyquist was for this wave or this spatial frequency where this is kx equals 1, we figured we needed 2 samples in each period. So we need a maximum, a minimum, a maximum, a minimum, and that's the Nyquist frequency. If we sample any lower than that, i.e. our samples are farther apart, we start getting these artifacts. This has an analog also in the theta direction. So if we're deciding how many theta views do we need, we can think of it in terms of this, in terms of the Nyquist criteria, but in the theta direction, not just the L direction, right? So let's look at this. Here we have a diameter of a field of view, which is 115 pixels in this diameter. It turns out that the diameter that matches our Nyquist sampling in the theta direction for this object, we can compute what that is from 180 views over pi by 2 gives us a radius or a diameter of 115 pixels. So just from the number of views we take, if they're evenly distributed, we can figure out at which radius that turns into the Nyquist criteria for sampling in the theta direction. And the diagram that we'll use to look at that is here. So this is in the spatial domain, X and Y. If this is a field of view, okay, we just looked at one. And I have my L direction here, and my detectors are separated, you know, by delta L, okay, in space. And we want to match that sampling rate. So it defines a sort of Nyquist sampling rate. As soon as you say, okay, this is my delta L, that tells you the maximum number of spatial frequencies you can measure in the L direction. So if we want to match that in the theta direction, then in this diagram, the distance between this point and this point should actually be delta L. Okay, and then we know that moving around in theta, I'm sampling at the same rate that I'm sampling along delta L. And that's a nice matched rate, okay? As I go farther out, obviously the delta S gets farther apart, and hence the sampling rate in theta goes down. Okay, so outside that field of view, my sampling rate is not high enough to include all the frequencies that I'm measuring in my delta L direction. Is that kind of clear how that's working out? And so you can just compute, whether you want to, you compute the number of views required, right, in order to, and under the assumption that they're evenly distributed, right, to determine when delta L and delta S are equal, and that gives you the field of view that will be inside the Nyquist criterion for the entire picture, right? So you set delta S equal to delta L, and then it gives you a formula basically for the number of views you need for that field of view. So we can look at this in a clinical scanner. Actually, I mean, the thing that I showed you before was a simulation that you can do, with that script. And does this actually happen in a clinical scanner? Well, yes, it does. In that you can see the noise properties here at the center of this image of it's essentially a water background. So it should all have a mean of 0. It has a mean slightly more than 0, but here with a standard deviation of 70 inside here. And then when we move to the periphery of this phantom, the mean doesn't change, but the standard deviation does, right? It goes down. So there's some kind of correlations occurring here that's reducing the standard deviation, right? And it's pretty obvious, at least on my screen, on your screen, it's pretty obvious too, that there's a structure that has this radial streakiness to it, right? In the estimate of the water background here. Whereas this structure, if there's a structure here, I don't know, there could be some kind of correlations in a circular way, but it doesn't look like there's radial streak structures here, right? It becomes actually even more evident when you take this phantom, and what we're doing here is we're making a movie where each frame of the movie is a new slice of the phantom. So it's a new instantiation of that picture. So it's a new version of the picture with new random noise on it, right? And it's really obvious now that the noise behaves quite differently in the middle of this phantom than it does at the periphery. And so when you're trying to evaluate what is my point spread function and what is my modulation transfer function and what is the expectation of noise correlations, right? It's different in the middle of this picture than it is in the periphery. And so in CT, to fully characterize the system, you want to make those measurements as a function of position, right, in the field of view. You can see that there are some, on occasion, there are some correlated circular structures in there, right, that you'd never see in MR, for example, right, these circular structures. And in MR, you very rarely see these streaks. MR has a simpler model for noise in that all of the noise its source basically comes from infinite bandwidth white noise that is thermal, right? And so that just gets plopped onto the scan. It does get modified to some extent if you start doing sophisticated acceleration techniques with MR and solving for different parts of the field of view given different coils and things like that. The noise can get more complicated, but at its heart, it's essentially a completely random set of numbers, right? It's, yeah.
Noise seems to be sort of swirling around the objects, but you can especially see it on the black spot.
Let's see, let me see what you're saying. Oh yes, that's called the black hole effect. Yeah, no, I don't know. I just made that up. But you're right, huh? Yeah. So, edges in CT are obviously a interesting thing, right? Because remember, in our projections, you know, if you have any kind of sharp change, when you do the convolution, that thing just amplifies up enormously, right? So unless you get the summation of all of those back projections spot on, you're going to see artifacts from edges. And what happens usually from an edge is it'll broadcast artifacts with a thing called a streak, right, off to somewhere else in the field of view. Here, this is really fascinating because it does look really local and it does look like it's spinning. This is a bit of a cheat because to do this absolutely correctly, I would have sat at the scanner and scanned like 500 images of the same slice and then just played the movie of the 500 images. The way I cheated here is I took a phantom that doesn't change in Z, like its structure doesn't change in Z, because these are, you know, cylindrical objects, and I'm just paging through those slices, right? So there could be other things happening here, slightly other things. For example, maybe the edge is just slightly moving across the field. It doesn't look like it is, but you know, that could be one thing that's happening. Yeah, it could be. It could be that you can see it because, you know, the edge is a different type of edge and the edge falls away as it. So we're kind of looking at the background being the top as opposed to the background being the bottom, right, of this artifact field. That could be. That's a great question. And you can see that on occasion, it's almost like there's an explosion of circles in the middle, right? Like boom, right there. So there's some kind of correlation. You know, maybe one detector in one slice was a little funky and they had to interpolate across it, and that caused that pattern, right? If they didn't interpolate across the bad detector, it would be a very bad ring artifact or something. But normally what they do is they scan through the data and say, oh, this detector is obviously bad, so we're going to drop it and we're going to interpolate its value, right? There's as many detectors there. Yeah. But it's a complicated business, right? It's not just like a simple, you know, mean field with white noise on the top. So yeah. Can you repeat the first part of the question if you can speak louder, because I can't see your mouth. So oh, what makes the contrast different? Got it. The dark one is more than likely air. Okay, so it's a hole, or it's got some kind of plastic ring, and then there's air inside. More than likely, it doesn't look like you visualize an edge of some kind of structure there. So I could be wrong there. It could just be a solid piece of something in water that has very low attenuation, right? So something with very low density, right? The really bright stuff it can be either higher density plastic, higher density doped plastic, if it's got some iodine or something like that in it. It can be, you know, crushed up bits of calcium and things like that, so that it's just a higher mu value. And so normally with these phantoms, they pick materials that have different mu values and such that it spans the relative contrast. These are all fairly high contrast from water, right? So, and then here you can, you know, you can have different simple things like different concentrations of iodine, although this looks like it's less than water. But who knows, maybe if this is plastic, right? And this is a hole, and this is water in the plastic, and these are water with iodine, could whole bunch of possibilities, right? Okay, so how you sample and how you reconstruct the data really affects the visualization or the sort of subjective quality and even the measurable quality of CT images. Right? So we have this ability to change sampling rates. But then when we get the data and as a vendor, we understand that this noise is really complicated and we try and reduce the noise, right? And increase the fidelity of the signal by saying we have a higher signal to noise image. We can manipulate the data to make that happen. And this is a very interesting component of CT in that if you look at MR manufacturers, when you look at one image to the next for manufacturers, they're basically the same, right? Most of it's all about ease of making the machine do what you want it to do. Right? In CT, the data goes into this black box that is at the vendor, and it comes out like this. And there's 3 different vendors up on the screen. Do you guys mind if I dim the lights a bit? Okay, that did something. Okay, so we're going to do a poll. Okay, so this is 3 different vendors, right? And they're quite different looking pictures, right? And so what would you do with these pictures? One of the things we would like to look at in these pictures, for example, is this object here, this little circle here, the little circle there, and that little circle there, and that little circle there. Those objects are the right coronary artery. Comes off the aorta and then wraps around the back wall of the heart. And you would like to measure actually the diameter of that object, right? Or visually, you would like to determine whether or not that little circle has a changing diameter as you move through it. Does it thin down and then come back? And if it thins down and comes back up, that means it's coronary artery disease, right? And so that's an object that is looked at a lot in cardiac CT scans like these. So radiologists go up and down, they'll have, say, 256 slices that look similar to this, and they roll up and down, as we'll see in a minute, through the heart and look at those vessels. So that's one thing. Another thing would be, where is the boundary between the blood and the myocardium? Precisely, where is that boundary? That's another thing you might want to do with this data. Another thing would be, what is the signal intensity of the myocardium itself along here? Because we've injected contrast. And if the contrast does not go into the myocardium does not increase its mu value. And that's an indication of poor blood flow in the myocardium, right? And so it's an indication of ischemia. So those are 3 possible things we would do with these pictures, okay? So I'm going to take a poll now. If you could only use one of these pictures, like to make your measurements, which one would it be? So who would prefer to read this picture? Put your hand way up if you want this one. 2, 4, 6. I got about 8 people want this one. Okay. Who would prefer to read this one? How about the same number? And who would prefer to read this one? Got 1, 2. Okay, so you guys are the outliers. Oh, you got 2 back there, but you're kind of like this. I was like, yeah, maybe. Yeah, I don't know. Maybe. So, I'm sorry. Yeah, I can't hear you. I'm sorry. So anyway, let me ask those people who picked this one. Who picked this one? You picked this one? Okay, why would you pick that one? It just looks great. Okay, that's a great reason. And principally, okay, and you think the resolution's higher because of what? Just think it's higher. Yeah, okay, yeah. 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 This one, because it's got the best contrast. Okay.
Boundaries are more defined as well. Boundaries are more defined.
Yes, and so the boundaries, and this is exactly what you perceived, right? Was like, wait a minute, look at these, look at this edge here, look at that edge here. It's so sharp. How did we make that happen? Right? So that's true. This thing does have really sharp edges, and it has sort of really constant values in the areas where it should be constant, right? So somehow the noise got reduced here compared to, say, this one, right? And the edges remained, right, sharp. So we didn't just average pixels together or convolve it with a Gaussian to make the variance go down and sacrifice resolution. Some magic happened here. And we've taken our own raw data from scans here and tried to reconstruct them so they look like this, and we have been totally unsuccessful. We tried like 10 different ideas, good ideas, and we can't recapitulate what's happening here. And the vendor certainly isn't going to tell us how they do it, right? So, but the complaint about this is that it looks sometimes like somebody's painted it, you know, that it's a representation of the object, but is it the object? You know, so it generates some skepticism in some radiologists when they look at it. They go, I don't believe that that's what that object is. Somebody put this on the page for me and it looks great, but it looks too good. You know? So who picked this one? Okay, what's up with that one?
If I had to pick one, just because it has like a very well contrast, so if I could get most information on
Okay, so there's a balance of, you can actually see the noise. That's what you're saying, and so now you have an idea of like how much noise there actually is in.
comparing it to one of the
Yeah. Right. So I think this picture is probably the most honest picture on the screen here, in the sense that it's closest to what you would achieve by really good quality imaging plus a standard reconstruction with maybe, you know, some kind of filter. It's not a Romlock filter, it's some kind of smoothing filter, but it doesn't do anything special to the signal, right? And then this one, who likes this one? Yeah, why do you like it?
I see a lot of like white, small, like dots.
Yeah. Okay. So these dots here, you're saying they're higher contrast, or they're more visible or something like that. Yeah. So there's no right answer to any of this, really. And when radiologists go to, there's a conference that's going to happen in a couple of weeks. It's called the RSNA. 60,000 people go to this conference. Half of the sales of radiology equipment for the whole year for most of these companies happen in 2 weeks, right? And the radiologists show up at this conference and they sit down and they look at these things and go, oh, that's your new pictures? Oh, cool. And that's how they make the decision. It's not like, let me get out where's my physics person? Let me, you know, do some tests on the point spread function and the MTF. And they're not going to ever go to this vendor and say, your MTF is 10% smaller at this spatial frequency, right? That's for us to figure out, you know, when you get the machine and you try and figure out what is it that you can actually state is your true resolution here. But the way these things are sold is exactly what you've all just done. Is you look at it and go, I have confidence that I can read that, right? And it happens all the time that you get, especially in CT, somebody will come from another institution and they've been working with these pictures, and then day after day you show them these pictures and they go crazy, right? They're just like, oh, we need to buy this other scanner because I used to love that other scanner. And it's almost like they art, you know, they say, I love Impressionists versus I love Rembrandt, you know, kind of thing. And this is more like Impressionism, but like high edge Impressionism, right? You know, so it's a fascinating field, and the ability of a vendor to create these pictures that not only have the underlying physics right, in that you know, the MTF is good and the PSF is good, but it also has this feel to it, you know. So that's a interesting conundrum. Usually not, in the sense that unless it spectacularly fails, they can go back, but there has to be some spectacular failure mode that nobody knew about. Right? So I've seen it happen, right? But it's not because everyone goes, oh, we thought we'd like it. That is not the way reason it goes back. And no, not a CT scanner, no. You can get as many example cases and pictures you want from the vendor. If you work with the vendor, they'll say, I want you to go visit this clinic. And usually with CT scanners, the clinic is like a mile away and they have a scanner there because there's so many of these things. So they say, just spend a day over there and you see 20, 30, 40 cases and see if you're comfortable with it, right? So that's one way of doing it. Yeah. Well, CT machines vary between $250,000 to $4 million, depending on the sophistication of the machine. The 4 million, there aren't many of those. They're like the new high-end photon counting machines and things like that. The median price, I would say, for these is probably about $1.2 million. Yeah, something like that, $1.5 million. Yeah, basically like an MRI, similar, although it's cheaper to install, and it's cheaper to make the room. Because MRI, you have to actually put the scanner in a Faraday cage. You have to make the room RF silent. So this is like, you go to these companies and the only people they usually build these for are like the CIA and people like that, right? Where you need a room that nothing gets out, nothing comes in. Because if you do MRI just out in space like this, you get tons of like marine band traffic, you know, and stuff like that in RF. So in CT, the basically you just plop it in a small room and you have to have enough concrete or some other material that absorbs X-rays so that there's no X-rays escaping from the room, but that's not expensive. But you know, one of the reasons why there's so many of these scanners is that, let's say the median billing for a CT scan is $450. You do one of these every 5 minutes in the United States. In Beijing, they do one every 2 minutes. They just like boom, boom, boom. They put so many people through these scanners. It's incredible, right? And so here, you know, to make up your $1.5 million doesn't take very long, right? So we got a scanner here. When I came here, we got this special scanner, and there was complaints about how much it costs and stuff like that. And I was like, yeah, I think you're gonna make your money back in like 6 months. So don't give me that complaining business. And you know, now we've done 29,000 studies on that scanner, and this was in 2016 we put it in. So just do the math. You know, it's paid for itself. Yeah.
So the signal could run out.
Yes.
Do they give you build like her ink white, or is it?
Oh, I see. So, well, an X-ray tube which is the source of your x-rays, right? It's like a light bulb, and you use it so many times and eventually it just does fail, right? And that's the most expensive thing that can happen usually in a CT scanner when it fails, is that you just need a new x-ray tube, but they're not cheap. They're like 50 grand, 100 grand, 200 grand, depending on how sophisticated the tube is. Usually manufacturers make a lot of guaranteed income by having a service contract on every device they sell. And so you put a scanner in and you pay literally up to 10% a year of the full price of the scanner to have a full service contract. And that means if anything goes wrong, they just replace it, right? You can try not to do that, but usually it works out better to do that. And that's, on the books for a medical imaging company, that's a remarkable, revenue stream, because it's you just write it down and it goes out for 4 years or whatever. It's just money shows up every month, So here's a comparison of what 2 CT scans look like in the same person when you use the maximum amount of X-ray fluence you can generate with the X-ray tube. And in our case, at 100 kVp, we can generate this 700 MA amount of X-rays. Now, the new tube we're going to get, that number would be 1200. Okay. And so with that amount of X-rays, you get a picture that looks like this. Interestingly, this image is from a sequence that was through the heart, and that sequence lasted 1 R to R interval of a heartbeat, so from 1 QRS to the next QRS. And then as it came up to the second heartbeat, it ramped down, the scanner ramps down the MA on sort of a continuous ramp as it's shutting off. You still have X-rays coming out, and so you can make a picture inside that ramp, right? And it turns out this is what a picture looks like at 24 MA. Okay, that was the average X-ray fluence while this picture was being taken. It was the same patient, heart's in the same condition, right? And that's what the picture looks like. Okay. So certain things are noticeable right away, is that obviously the random noise there has a higher fluctuation amplitude. But also the manufacturer, it's fairly obvious when they have raw data that has so few photons in it, they do a lot of smoothing in that raw data. Because when you look at this picture, it is a lot smoother than the one on the left, right? So it's not just a reduction in numbers of photons and an increase in noise. They also go in there and say, well, in this area, we got too few photons, we're going to start interpolating a lot of stuff, and you get a smoother picture. And it's very hard to disarticulate when you have a commercial scanner. What does your signal to noise do when you reduce the number of photons? Because there's a little demon in the back who keeps on messing with the data to keep the signal to noise about the same, if possible. And so that's, however, the interesting thing here also, right, is that this is a huge reduction in X-ray dose. And we're getting a reasonably good picture for virtually no X-ray dose, right? 24 MA, it would give you a dose of like 0.05 millisieverts or something. It's like a epsilon change in your annual dose absorption. And yet the picture, depending on what you want to do, is probably adequate. So what is it adequate for? If you were looking at, does this patient have a heart that is the right basic shape and it is moving in the right way? Probably that's good enough, right? Because you have these large features. If on the other hand, you wanted to tell me, is this vessel open? right? So that's the LAD running all the way down towards the apex of the heart. So it's a very small diameter because it's run a long way. Okay, well, let's go over and see what's over here. Oh, well, no. I'm not gonna make that call, right? Because you get a whole bunch of things over here that could be a vessel. And so you just can't do that. Okay, so we'll look at a couple of imaging artifacts. Again, so this is along the same lines of two images of the same patient. What happened here is, the image was taken, it came up on the screen, and obviously the tech looked at it and said, oops, that's a bad idea, because we have all of these streak artifacts. And either the patient didn't know or they didn't instruct the patient, but the patient's arms were down by their side, right? And the arms are out here and here, and that is outside the field of view, essentially, right? So the detector, when I have my source here and I'm, taking data on my detector, it doesn't see the arms, right, for these views. And then when my detector's over here, the X-rays go through both arms. So now you have some very inconsistent data, right? Because things are coming and going onto the detector, as you rotate the thing. And so that's not a good situation. So you lift the arms up and all of that goes away. All the data is consistent, right? Another image artifact is, now this is a little confusing because this direction here, remember, is Z, okay? So going back to our detector, this is, for us, with the scanner we have here, it's 256, detectors this way. The L direction, or the 1000 direction, is going into the plane of this picture, okay? And this cone beam is rotating around the patient. But you can see that if our source is here, I mean, this is an exaggerated drawing, but, and it comes out onto our detector here in Z, this little chunk of tissue right here in the patient gets projected onto our detector at this angle, but then 180 degrees later, when the X-ray beam looks like this in Z, it is ignored. It doesn't project onto the detector. And so the result of that is that the field of view you can image with CT in the Z direction actually looks kind of like a football, right? In that it pinches down, right? You can only produce images of things that you've got, a full set of projections from. So that's partial volume artifact in Z from these thick detector scanners, right? And now this is probably the most common artifact that is seen in CT. And it's called beam hardening. And this, we're going to step back to a lecture, maybe 4 lectures ago or 5, where we looked at the source of X-rays. And if you recall, the relative number or relative fluence of X-rays at specific energies of the X-ray photons, that it looks like a function like this. If I set my voltage to 120 kilovolts, it's 120 kVp is the highest energy photon I can get, but the relative numbers of photons as a function of energy looks like this. And remember, it goes down to 0 here because we filter out the low energy photons. We filter them out with either copper or aluminum, a little, maybe a few millimeters of copper or aluminum, and the glass and other things. So this is the energy spectrum. Excuse me, I'm gonna cough. There. This is the energy spectrum, right, at 120 kVp. That's what comes out of our X-ray tube. When you look at what happens when that beam enters an object or a patient, and let's ask the question, what does the energy spectrum look like when it hits this pixel, right? So if my source is over here and the X-rays are traveling through the patient this way, by the time I get to that pixel, many of these low energy photons are gone. And the reason is there's a much higher probability that they get absorbed, right? And so the mu value, if you look at a table in the NIST tables, the mu value here at these high energies is different than it is at the lower energies. In fact, tissue does not absorb the higher energy photons as well as it does the lower energy. And so what this pixel sees as its incident beam has been changed. Its energy spectrum has been changed by the flight path through the patient to there, right? And that's called beam hardening, because the relative number of high energy photons is higher here than it was when it entered the patient. Okay. And so when you ask, well, this pixel, what does it contribute to the relative attenuation of the total beam as I go through? When I go through on this path, it's going to be different than when I go through on this path, because I've only passed through, say, a few centimeters of tissue this way. And so when I ask the question, well, how much attenuation does the material in this pixel contribute this way? It's looking at a much softer or lower energy beam. And so it will attenuate more, right? So those two numbers are different. Physically, they're just different, right? And so the data itself is inconsistent in that way. Yeah. Yeah, sort of, but you know, average in what sense? I mean, because each projection is like a unique, you know, data set that is combined with back projection, right? And so the fact that you have a projection that is at 180 degrees, right, and should explicitly be a mirror image of the projection from the other 180, it turns out it is not, right? And so those things you could say, well, if I just back project this and back project that, I would just get the average, right? But then there's inconsistencies of what it gets from every angle, right? So you can correct for this in the sense that you can make a picture, your first, you know, estimate, measure all those mu values, and then compute what those differences would be, and you correct the data that way. An example is if we image just a cylinder of water, and so this is X and Y, and Z is into the page, and we don't do any compensation for beam hardening, then the image looks like this. And so the question is, why does it look like this? It's because all of these pixels in the middle, the only beam they ever see has traveled through half of the darn phantom first, right? And so it's been hardened on its way to this location, right? And whereas these ones out here, they, you know, see the X-rays as soon as they enter. They also see X-rays coming across this way, etc. And so this artifact shows up in a uniform phantom as this cupping, and then after you go in and correct for it, you tune your correction such that this turns out to be flat, right? So that's seen a lot in because you can't get this perfect for very complex objects often. And then when you have something that's a really high attenuator that takes away a lot of the beam, you get streaks, and that's a metal artifact basically. Yeah.
in my view, it looks like the result should be imbalanced. The signal from the two opposite views.
Well, the reason it's symmetric here is because the object itself is completely symmetric, right? For this process. So I have, you know, depending radially on where I am, I will have experienced exactly the same beam hardening effect as all of my pixels that are on the same circular path here, right? Because that set of views will look identical for all of us, right? So there's not, you know, if you know, for this object, it just has that symmetry, right? So okay, so we can look at some advanced applications. We got 3 minutes. This is CT imaging of lung nodules. And so it's been shown that this is a big application now, that if you're a smoker and you're above 50, that you should have a CT scan to look for cancer in your lungs. And if you do, if you take a whole bunch of smokers and do this, the total number of people that die in that pool actually goes down because you discover cancer early. If you do it in people who don't smoke, it doesn't really have much of an effect because you don't detect it very often, right? So, but these nodules, these little things, you know, are the things that you're after when you do this screening. And this is a very interesting paper. You guys are welcome to download this and read it. 12 out of 13 radiologists caught this one, right? 8 out of 13 radiologists caught this one. And then 5 out of 13 caught this one, and only 2 out of 13 caught this one. Right? And so you can see why, you know, it looks like all the vessels around it, right? So it's pretty simple as to why this thing, you know, wasn't called. I think if you called this, you'd be calling wrong ones fairly often, right? Because you'd be calling vessels, et cetera, et cetera. And who knows, maybe the 2 that called this actually thought this was the, you know, we don't know. So I think what this shows is that anything that a human does and the human zips through the data and can do it in about 30 seconds, 15 seconds, we're going to have deep learning networks do it, right? And that is, the reason is you can generate millions of these cases where you know the outcome of the case, and you can train the network on those cases. And it's very hard as a human to read 1 million cases and get trained, right? So what we're seeing is that a clinician will have sitting beside them, it won't be a resident who's read like as many as they can, or a fellow. It'll be this machine that just says, hey, you should take a look at this thing, because, you know, I got a 50-50 shot. This is abnormal. And then you can get in there and take a look at it. So this is one of the areas where I think broad spectrum deep learning is a big deal. Here's another application that's sort of an advanced application in our last, when do we go to? 12:20, right? Yeah, okay, good. We're in no rush then. And if you look at the raw CT in this, now you take a 3D CT of this person's lungs, and now we're cutting it in the coronal plane. So we're cutting it down this way. So we're looking from the patient's top, their chest down. And I don't know, can you see that on your screen? Is there a difference between this and this? Other than the fact the aorta is here. But you can see, right, that there's this actually just looks darker, right, than this. There seems to be a higher baseline level signal here, right? And the reason for that is there is a lack of perfusion to the right lung in this patient. And one of the ways, so if you're comfortable as a radiologist, you can read this and you're confident that, hey man, this asymmetry tells me that this is, there's a perfusion deficit here. That's fine. You can also quantitatively do it by injecting a dye or a contrast agent, and then looking and seeing how the signal in the lung parenchyma changes as a function of time. And in fact, solving for the amount of iodine, the iodine concentration in each, square centimeter in that lung. And when you do that, you get a map that looks like this, which, pretty well tells you the severity of the drop in perfusion in that part of the lung, right? And so then this, you would go back and say, okay, this person has some kind of, thrombus upstream, and we got to go find it, right? And I'll open that thing up. Dual energy is used to isolate the signal from iodine by looking at the change in the signal when you take a low energy, like a soft X-ray beam picture, and a high energy picture. Okay, so you take those two pictures, okay, and each tissue will respond differently to the change in energy, like the fractional change in the intensity at that voxel, depending on the material, will be dependent on the mu values of that material at those two different energies, right? And so you can arithmetically, algebraically recombine those two pictures such that the change in the high energy and lower energy for iodine and bone, say, are highlighted, and it gives you essentially a direct estimate of the amount of iodine in that voxel, right? So we've been using this actually quite a bit in patients who come in with lung disease, or there's a disease that it's treated a lot here at UCSD called CTEF, which every CTEF patient before they have their surgery gets one of these pictures, essentially to see where the reduction in blood flow is severe. And then here's an example of one manufacturer's shot at taking super high resolution pictures. And they took the standard detector that basically all manufacturers used. It wasn't the same manufacturer of the detector, but it was the same geometry. And that is, each element is separated by about 1 millimeter. And they said, well, we're going to take each element and cut it into 4 by reducing it in 2 dimensions, right? So now our new detector looks like this, right? So it's a big jump and a gutsy move for a number of reasons. But the question is, can you see any new features that are going to be clinically relevant? And here's a very fine, small, nodule in the lung. And this is what it looks like under normal resolution. And this is what it looks like with this new detector, right? And, question, can you see new things? Well, if you look at these small airways, this little airway here, this airway here, also there's one here, there's one here, there's one here, and these tiny vascular structures here, the airways certainly are just not visible here. And, the border of this bright zone plus the texture of the tissue itself, it looks like a very smooth, constant texture, as opposed to something that had a rougher quality that you would not be able to detect up here. So, I think definitely there's remarkably new information here. One of the caveats, though, is in order to get these, you need to reduce your spot size on your X-ray tube down to at least sort of this size, right? And so now we've got 1/4 of the rectangle trying to make the same number of x-rays, right? In fact, maybe make more x-rays because we need to measure them in these pixels, right? And so that's a big ask to make an x-ray tube like that, but they did. And this scanner, I think, works terrifically well in pretty thin people, like smallish people, right? If you're a really big person, it's hard to make enough x-rays with that tube to get through. So here's the comparison, and it's obvious that you're seeing things over here that just don't show up over here. And here's an example using that same detector of a cardiac image, and the detail in the coronary vessel and the wall of the left atrium here, the valvular structure of this, look at the aortic valve here and the little piece of calcium that shows up there. It's absolutely spectacular, right? That resolution. It's something that is unusual to see in a cardiac CT scan. And in this patient, actually, this scan was a experimental scan at the NIH. So they did a patient in this scanner plus another scanner 6 months later. And so here's a bit of a coronary vessel with a very bright piece of calcium. And that's what the calcium looked like in the standard scanner, right? So, you can visualize things just better. But again, it comes with the caveat that you need to be able to get the x-rays through this patient with the small spot size.